Welcome everyone to tonight's journey off science to sleep by across the stars. As you settle into rest, let your mind drift outward beyond the familiar constellations, past the glowing band of the Milky Way stretched across the night sky. We're going to explore a simple but profound question. How far does our galaxy actually reach? Together, we'll glide from the bright spiral arms near our sun, through the vast, dim halo of stars, and into the mysterious realm of invisible matter that holds it all together. This isn't just science, it's a lullaby sung by the universe itself. So close your eyes, breathe deeply, and let's wander through the Milky Way. When we look up at the night sky on a clear, dark evening, far away from the glow of city lights, there is a silvery band that stretches across the heavens. It is faint and delicate, yet also impossibly vast. This is the Milky Way, our home galaxy, seen from the inside. To the naked eye, it looks like a misty river of stars flowing across the sky. But in truth, it is the grand structure in which we reside, made of hundreds of billions of stars, swirling gas, invisible dark matter, and mysteries beyond measure. To understand how far our galaxy actually reaches, we must first understand its shape, its design, and the way its structure unfolds across space. This is not a simple sphere of stars floating in the void, but an intricately layered system that tells a story of billions of years of cosmic evolution. The Milky Way is what astronomers call a barred spiral galaxy. Imagine a vast pinwheel turning slowly in space, its arms unfurling like ribbons, extending tens of thousands of light years from the center. At its core lies a dense, elongated feature known as the bar, a structure made of tightly packed stars that stretches across the galactic center like a glowing bridge. Surrounding that bar is a bulging, rounded region filled with older stars, a crowded environment where ancient stellar populations live and die in a chaotic and brilliant dance. This central bulge is the heart of our galaxy, and deep within it lies something even more enigmatic, a supermassive black hole known as Sagittarius A, weighing millions of times more than our sun, anchoring the Milky Way with its immense gravitational pull. From that glowing center, the spiral arms begin their graceful sweep outward. These arms are not solid structures, but regions of enhanced density, like traffic jams in the flow of stars and gas. As material moves through these arms, clouds of gas are compressed, triggering the birth of new stars. This is why the spiral arms shine so brightly in certain wavelengths of light. They are dotted with hot, young stars, brilliant clusters, and glowing nebulae where stellar nurseries are at work. Our own sun is not located in one of the main arms, but rather in a smaller, less prominent spur known as the Orion arm, or sometimes the Orion spur. From our vantage point, it is like living in a quiet suburb of a great cosmic city. Not too close to the bustling center, not too far into the dim outer reaches, but in a place where we can look both inward and outward. But the galaxy is not just a flat pinwheel painted on the canvas of space. It has depth, layers, and hidden structures that make it far more complex. The spiral arms form what is known as the galactic disk, a flattened region where most of the stars reside, along with gas and dust. This disk is about 100,000 light-years in diameter, which is an almost incomprehensible span. To put this in perspective, if you could travel at the speed of light, the fastest speed the universe allows, it would still take 100,000 years to cross from one side of the disk to the other. And remember, that is only the span of the disk itself. The galaxy extends far beyond. The disk is also relatively thin compared to its width, only about 1,000 light-years thick, though it flares outward toward the edges, like a vinyl record with slightly warped sides. Above and below this thin disk lies another structure, the galactic halo. Unlike the bright, structured spiral disk, the halo is a sparse and diffuse sphere of stars, clusters, and dark matter that envelops the galaxy. It does not glow with the same concentrated light as the disk because the stars here are older, fainter, and fewer in number. Yet, in its sparseness lies something profound. It extends far beyond the spiral arms, possibly as far as 300,000 light-years from the center, forming a kind of invisible shell that defines the true reach of our galaxy. Within this halo are globular clusters, ancient collections of stars bound tightly together, orbiting the galactic center in vast, sweeping paths. These clusters are relics from the earliest days of the Milky Way, fossils of cosmic history that remind us of the galaxy's great age. And still, even this description of the halo does not fully capture the Milky Way structure. There is also the dark matter halo, an even larger and more mysterious component. Dark matter is invisible, indetectable by light, but its presence is revealed by the way it influences the motion of stars and gas. Without dark matter, the galaxy would fly apart. The visible stars and gas simply don't provide enough gravity to hold the galaxy together at the speeds we observe. Scientists believe that the dark matter halo may extend well beyond the visible stars, perhaps 1,000,000 light-years from the galactic center. This means that the galaxy's true shape is not just a glowing pinwheel of stars, but an enormous, invisible sphere of mass, within which everything else is suspended. The Milky Way structure also includes faint streams of stars, remnants of smaller galaxies that have been torn apart and absorbed by our own. Over billions of years, the Milky Way has grown by devouring its neighbors, pulling them in and stretching their stars into long, thin trails that wrap around the galaxy. These stellar streams weave through the halo like threads in a tapestry, further extending the reach of the galaxy's influence. Our galaxy is not a static thing, but a dynamic, living system, constantly reshaping itself through cosmic encounters. If you were to step back and view the Milky Way from a great distance, from outside its luminous disk, what you would see is a barred spiral with 4 primary arms, a bright core, and a hazy halo of scattered light. You would see a structure with order and symmetry, but also with irregularities, the scars of past collisions, the warping of its disk, the streams of stars like brushstrokes across a cosmic canvas. You would see a galaxy that is both elegant and turbulent, orderly and chaotic, a balance of gravity and motion stretched across 100,000 light-years. And here we are, tiny inhabitants within this colossal structure, trying to map it, to understand it, to measure how far it reaches. From our vantage point inside the disk, our view is obscured by gas, dust, and distance. We cannot step outside to take a snapshot of the whole. Instead, astronomers piece together its shape by studying the light of distant stars, by tracing the faint glow of hydrogen gas, by mapping the motion of clusters and streams. Slowly, with patience and persistence, a picture emerges: the Milky Way as a barred spiral galaxy, with a luminous disk, a bright bulge, a faint halo, and an invisible envelope of dark matter. It is a structure both familiar and alien, something we think we understand yet know we only partly grasp. The Milky Way is our cosmic address, the grand architecture of our home in the universe. Its shape is not just a scientific curiosity, it is the stage on which our entire history has played out. From the formation of the sun and earth, to the rise of human consciousness, to this very moment where you rest and imagine drifting among its stars. To ask how far our galaxy reaches is to begin by tracing its form, by unfolding its spiral arms, by stepping into its halo, and by acknowledging the invisible presence of dark matter that holds it all in place. When we talk about the Milky Way, most of what we imagine and most of what we can see with our eyes and telescopes belongs to the galactic disk. This is the broad, flat structure that defines the luminous body of our galaxy. The part that holds the spiral arms, the star-forming regions, the glowing nebulae, and the majority of the stars that give the Milky Way its iconic appearance in the night sky. If the halo is the invisible skeleton and the bulge is the crowded heart, then the disk is the vibrant, living skin of the galaxy, the part that makes it look like a glowing pinwheel spread across the depths of space. Understanding the disk and its vast span is essential, because it sets the first boundary we can recognize when we ask ourselves how far our galaxy actually reaches. The disk is immense. Astronomers estimate that it stretches across about 100,000 light-years from edge to edge, though some studies suggest it may be even larger, perhaps 120,000 or more. This number alone is staggering, because a light year is already such an incomprehensible measure. Light, which travels faster than anything else in the universe, takes one full year to cross just a single light year. Multiply that by 100,000, and you begin to get a sense of how wide the disk really is. Within this span lies nearly everything we associate with the Milky Way: billions of stars, immense clouds of hydrogen gas, lanes of cosmic dust, and the spiraling structure that gives our galaxy its elegant form. The disk is not simply a uniform sheet of stars. It has layers, thickness, and subtle variations. At its core, the disk is relatively thin, perhaps only 1,000 light-years thick in most regions, making it look very much like a flat, spinning record suspended in space. However, the disk is not perfectly flat. It warps, bends, and flares at the edges. Imagine a vinyl record left out in the sun, where the edges curl upward or downward slightly. That is not far from how the Milky Way's disk behaves. This warping is likely the result of gravitational interactions with nearby galaxies, particularly the Magellanic Clouds, which tug at the Milky Way's edges and disturb its perfect symmetry. This subtle distortion is one of the clues that the disk is not a static and changing structure, but one that responds to external forces, shifting and flexing over cosmic timescales. Embedded within the disk are the spiral arms. These arms are not rigid structures, but patterns formed by density waves, regions where matter is temporarily crowded together as it orbits the galactic center. In these regions, clouds of gas are compressed, triggering bursts of star formation. This is why spiral arms are often dotted with luminous, young, massive stars that burn hot and bright, giving the arms their distinct glow. The Orion arm, where our sun resides, is one of these smaller structures branching between larger arms. It is in this neighborhood of the disk that humanity evolved, far from the tumult of the central bulge, yet close enough to see the richness of the galaxy's structure unfold across the sky. The disk is not only about stars, but also about the material that forms them. Between the stars lie vast reservoirs of interstellar gas and dust, a medium that astronomers refer to as the interstellar medium. These clouds are often invisible in ordinary light, but they glow brightly in radio and infrared wavelengths. Some are dark and cold, absorbing starlight and appearing as shadowy patches against the brighter background. Others are brilliant nebulae, illuminated by the intense radiation of nearby newborn stars. The disk is therefore a place of continual transformation. Stars are born from gas clouds. They live their luminous lives, and they return material back into the interstellar medium when they die, enriching it with heavier elements forged in their cores. This ongoing cycle of birth and death is one of the defining features of the disk and a primary reason why it glows so brightly. It is within the disk that the Milky Way displays its diversity of stellar populations. Some regions are dominated by ancient stars, faint and red, living quietly on the outskirts. Other regions sparkle with brilliant blue giants, massive stars that will live only a few million years before collapsing in spectacular supernova. Clusters of stars, both open clusters and associations, dot the disk like jewels, marking sites where groups of stars form together from the same cloud. Meanwhile, great dark lanes of dust streak across the spiral arms, blocking starlight and giving the Milky Way's band its patchy, textured appearance when viewed from Earth. The Sun itself is a disk star. It resides about 27,000 light-years from the galactic center, orbiting within the Orion arm. Our position gives us a special vantage point, not too close to the crowded center, where gravitational chaos and radiation would make life more difficult, and not too far in the dim outskirts, where star formation slows and heavy elements are rare. From this place, we can look inward toward the dense bulge and outward toward the spiral arms, seeing the galaxy stretch around us in both directions. It is this view, seen on dark nights as the Milky Way's band crossing the heavens, that has inspired human imagination for countless generations. But the disk is more than just stars and gas. It is also motion. Every star, including the Sun, orbits the galactic center, carried along by the galaxy's gravitational pull. The Sun makes one complete orbit roughly every 225 million years, a journey that takes it through spiral arms and across regions of different density. The entire disk rotates as a great system, though not like a rigid wheel. Instead, stars at different distances move at different speeds, creating the spiral patterns that define the Milky Way's appearance. This rotation is one of the keys to understanding the galaxy's mass, because the speeds we measure cannot be explained by visible matter alone. It is in studying this rotation that astronomers first found strong evidence for the existence of dark matter, a hidden mass that extends beyond the disk and shapes its motion. The disk's vastness is both awe-inspiring and humbling. Imagine setting off from the Sun and trying to travel across the disk at the speed of light. You would pass star after star, cluster after cluster, nebula after nebula. You would move past regions of dense star formation, through dusty clouds, across the great spiral arms, and after tens of thousands of years, you would finally approach the far edge. And yet, after such a journey, you would only have crossed the luminous disk, not the full extent of the galaxy. Beyond lies the halo, the faint outer regions that expand the Milky Way's reach even further into the void. From Earth, the disk is the part of the galaxy we see most clearly. It is that glowing river of light across the night sky, the plane in which our solar system resides. Its stars are so numerous and so distant that their light blends together into a diffuse glow, punctuated by brighter individual points. When you lie back under the stars and gaze upward, what you see is a cross-section of the disk, an inside view of its crowded interior. Every twinkle of light is a sun like ours, and every dark patch is a cloud of dust hiding more stars behind it. The disk is not just the structure of the Milky Way, it is the canvas on which our view of the universe is painted. When most people imagine the Milky Way, they think of its spiral arms glowing in the night sky, or the dense starry bulge at its center. But beyond the luminous disk and the familiar, photogenic parts of our galaxy lies something far more elusive and even more immense: the galactic halo. The halo is not as easy to picture as the disk because it is not bright or obvious. It does not have glowing bands of stars that can be easily traced, nor does it sparkle with the same vibrancy as the arms. Instead, it is faint, ghostly, and difficult to measure. Yet, this halo, and what lies within it, defines much of what the Milky Way really is. If the disk is the visible face of our galaxy, then the halo is its invisible body, a vast, spherical component that stretches far beyond the spiral arms and sets the stage for the galaxy's true reach. The galactic halo can be thought of in two overlapping forms: the stellar halo and the dark matter halo. The stellar halo is made of ancient stars, globular clusters, and faint streams of stellar debris left behind from galaxies that the Milky Way has consumed. These stars are sparse compared to the dense populations in the disk. They are often old and metal-poor, meaning they formed early in the galaxy's history, long before heavier elements were widely distributed across the cosmos. Some globular clusters in the halo are among the oldest known structures in the universe, containing stars that have been burning quietly for over 12 billion years. They orbit the galactic center in wide, sweeping ellipses, moving far above and below the galactic plane, like cosmic satellites bound to the Milky Way's gravity. From Earth, we cannot simply look out and see the halo the way we see the disk. The stars are too spread out and faint to form a clear band of light. Instead, astronomers detect the halo by carefully observing the motions of stars, by studying the faint glow of globular clusters, and by tracing streams of stars that arc across the sky. One famous example is the Sagittarius stream, a vast trail of stars ripped away from a smaller galaxy that was absorbed into the Milky Way. These stellar streams tell the story of how our galaxy has grown over billions of years, swallowing smaller galaxies and incorporating their stars into its halo. Every faint thread of light in the halo is evidence of a cosmic merger, a reminder that the Milky Way is not static, but constantly evolving. Yet even when we account for all the stars, clusters, and streams, something is missing. The visible matter in the halo does not explain the full mass of the galaxy, nor can it account for the way stars in the disk orbit the galactic center. If the Milky Way were made only of the stars and gas we can see, the outer stars should orbit much more slowly than they do. Instead, they move at speeds that suggest there is far more mass holding them in place. This hidden mass is what astronomers call dark matter, and it dominates the halo. Dark matter cannot be seen directly. It does not emit, reflect, or absorb light. It is invisible to every telescope we build, but its gravitational influence is undeniable. By studying the rotation curves of galaxies, astronomers discovered that the visible matter is only a fraction of the total. The rest must be something unseen, a mysterious form of matter that outweighs normal stars and gas by a factor of 5 or more. In the case of the Milky Way, the dark matter halo may extend out to 1 million light-years from the galactic center, enveloping not only the disk and the stellar halo, but also many of the nearby dwarf galaxies that orbit our own. This means that the true size of the Milky Way is far larger than the glowing spiral we can see. It is, in reality, a vast invisible sphere of mass, dictating the motions of everything within it. The presence of this dark matter halo reshapes the way we think about the galaxy's reach. The disk, at 100,000 light-years across, seems enormous, but it is only a fraction of the full structure. The halo, dominated by dark matter, may be 10 times wider. This means that most of the galaxy's matter is not in the stars we see or the gas that gives birth to them, but in an unseen component that remains one of the greatest mysteries in modern astrophysics. Scientists do not know what dark matter is made of. It could be exotic particles that interact only weakly with normal matter, or it could be something even stranger, a fundamental aspect of the universe that we have yet to comprehend. Whatever its nature, it defines the Milky Way's gravitational boundaries and sets the stage for its interactions with other galaxies. The halo also plays a crucial role in how galaxies form and evolve. Without dark matter, the Milky Way might never have come together in the first place. In the early universe, shortly after the Big Bang, matter was distributed in a nearly uniform way. Normal matter alone would have struggled to clump together fast enough to form galaxies. But dark matter, immune to radiation and able to collapse under its own gravity, formed vast scaffolds in which normal matter could collect. These scaffolds, invisible to us but detectable through their effects, guided the formation of galaxies like the Milky Way. The halo, then, is not just an afterthought or an outer layer, it is the very foundation upon which our galaxy is built. Even now, the halo shapes the Milky Way's future. The stars and clusters within it trace out the history of galactic mergers and collisions. Streams of stars arc across the halo as reminders of smaller galaxies that were consumed, and more such mergers are still to come. The Andromeda galaxy, our nearest large neighbor, also has its own massive halo of dark matter, and the two halos are already overlapping. This means that, long before the disks of the Milky Way and Andromeda collide, their invisible boundaries are already touching, their gravitational spheres of influence blending together in preparation for a future merger billions of years from now. The halo is not uniform or simple. It is clumpy, shaped by past interactions, dotted with substructures left behind from long ago collisions. Dwarf galaxies, some still intact and others torn apart, orbit through the halo like small moons around a giant planet. Each one feels the pull of the Milky Way's gravity, each one shaped by the dark matter cocoon that surrounds it. The large and small Magellanic Clouds, visible in the southern hemisphere as glowing smudges of light, are two such companions, slowly spiraling closer under the influence of the Milky Way's halo. Their interactions with our galaxy create ripples and warps in the disk, reminders that the halo is not a passive shell, but an active participant in galactic dynamics. To study the halo, astronomers turn to clever techniques. One is gravitational lensing, where the mass of the halo bends the light of more distant objects, revealing the presence of unseen matter. Another is the careful mapping of star motions using missions like Gaia. which track the positions and velocities of billions of stars across the Milky Way. By observing how stars move through the halo, scientists can infer the distribution of dark matter and better understand the true extent of our galaxy. Step by step, a picture emerges: the Milky Way as a luminous disk and bulge, embedded in an enormous, invisible halo that stretches far beyond what the eye can see. For us here on Earth, the halo may seem remote and abstract, but it is the reason we exist in the form we do. The Sun and its planets orbit stably within the disk because the galaxy is held together by the mass of the halo. The elements that formed Earth and life were forged in earlier generations of stars, whose remnants were dispersed through the halo and recycled into new stars. The invisible boundaries of the halo determine the Milky Way's gravitational reach, defining which dwarf galaxies orbit us and which are beyond our control. Even though we cannot see it, the halo shapes our cosmic neighborhood and connects us to the larger structure of the universe. Beyond the luminous spiral arms, past the swirling lanes of gas and dust that define the galactic disk, lies a quieter, more ancient realm of the Milky Way. This region is home to the outer stars and globular clusters, stellar populations that stretch far beyond the bright, crowded interior and extend into the galaxy's faint outskirts. While the disk and bulge make up the familiar face of the Milky Way, it is in these outer regions that we find some of the oldest stars in existence, cosmic relics that have orbited the galactic center for billions of years. Their presence not only tells us about the galaxy's size, but also about its history, its growth through mergers, and its deep connection to the earliest chapters of the universe. Globular clusters are among the most striking features of the outer regions. These are tightly bound groups of stars, often containing hundreds of thousands of members, held together by their mutual gravity in dense, spherical swarms. Unlike the open clusters in the galactic disk, which are loose and short-lived, globular clusters are ancient and enduring. Many are more than 12 billion years old, meaning they formed when the universe itself was still young, less than a billion years after the Big Bang. To look at a globular cluster is to gaze into a time capsule, a gathering of stars that has remained intact across cosmic epochs while galaxies collided, grew, and changed around them. The Milky Way contains over 150 known globular clusters, scattered across its halo like ornaments around a cosmic tree. Some lie relatively close to the galactic center, but many extend tens of thousands of light years outward, marking the farthest reaches of the Milky Way's stellar population. These clusters orbit the galaxy in elongated, tilted paths, cutting across the disk at odd angles, circling far above and below the galactic plane. Their orbits are not confined to the orderly rotation of the disk. Instead, they trace the deeper gravitational field of the galaxy as a whole, moving like ancient wanderers, bound not to the arms, but to the invisible mass of the halo. Each globular cluster is a miniature galaxy in its own right, dense and crowded with stars. If you were to live inside one, the night sky would look unimaginably different. Instead of the sparse scattering of stars we see from Earth, the heavens would be ablaze with hundreds of thousands of suns, many so close that they would outshine our brightest constellations. Yet despite this dazzling density, globular clusters are not places where planets and life are likely to thrive. Their crowded interiors make gravitational interactions frequent, disrupting planetary systems and making stability rare. Instead, their importance lies in their history and their role as markers of galactic structure. The stars within globular clusters are old and metal-poor. In astronomy, metals refer to all elements heavier than hydrogen and helium, and their abundance tells us when and how stars form. The early universe contained mostly hydrogen and helium, and heavier elements were built up only later, inside stars, and then scattered by supernova. Stars and globular clusters contain very few heavy elements, showing that they were born before the galaxy had been enriched by many generations of stellar life and death. This makes them among the first building blocks of the Milky Way, survivors from an era when the galaxy was just beginning to take shape. But globular clusters are not the only denizens of the outer Milky Way. There are also individual stars, faint and scattered, orbiting far beyond the disk. These halo stars are often just as old as the cluster stars and provide further evidence of the galaxy's ancient origins. Many of them are thought to be remnants of dwarf galaxies that were absorbed by the Milky Way long ago. When smaller galaxies collide with larger ones, their stars are stripped away and spread out into the halo, forming faint streams and dispersed populations. In this way, the outer stars tell a story of cannibalism, of the Milky Way growing by consuming its smaller neighbors. One of the most famous examples of this process is the Sagittarius dwarf galaxy, which is currently being torn apart and incorporated into the Milky Way. Its stars are stretched into a long stream that wraps around the galaxy, blending with the halo and adding to the population of outer stars. This is not an isolated event, but a common one in galactic history. Over billions of years, the Milky Way has absorbed numerous smaller galaxies, and each one has left its signature in the halo as scattered stars, clusters, and streams. By mapping these structures, astronomers can reconstruct the galaxy's history, tracing back the mergers and collisions that shaped its growth. The reach of the outer stars and globular clusters is vast. While the disk extends about 100,000 light-years, the halo populated by these ancient systems stretches 2 to 3 times farther. Some globular clusters lie over 200,000 light-years from the center of the galaxy, marking the true outer limits of the Milky Way's stellar influence. Beyond them, the stars grow sparse, blending gradually into the intergalactic medium, where the Milky Way's gravitational pull competes with that of neighboring galaxies in the local group. These remote clusters serve as boundary stones, faint markers of where our galaxy begins to fade into the greater cosmos. Studying the outer stars and clusters is not easy. They are faint, distant, and spread across the sky in subtle ways that are difficult to detect. For centuries, only the brighter clusters were known, catalogued as fuzzy patches of light in early telescopes. It was only in the modern era, with powerful observatories and space-based instruments, that astronomers began to map the halo in detail, uncovering streams, shells, and far-flung stars that reveal the true extent of the Milky Way. Missions like Gaia, which measures the positions and motions of over 1 billion stars, are revolutionizing our understanding of these regions, showing us not only where the stars are, but how they move through space, and thus revealing the invisible shape of the galaxy's gravitational field. The significance of these outer populations extends beyond our own galaxy. By studying globular clusters and halo stars, astronomers gain insight into galaxy formation in general. Nearly all large galaxies are surrounded by similar halos of ancient clusters, suggesting that this is a universal feature of cosmic architecture. The fact that globular clusters are so old and widespread means they must have formed early in the universe, before galaxies themselves were fully assembled. In this way, they provide a bridge between the early universe and the mature structures we see today. Each cluster is a fossil, a preserved remnant of the conditions that existed more than 10 billion years ago, when the first galaxies were taking shape. And yet, for all their scientific importance, there is also something deeply poetic about the outer stars and clusters. They are the loneliest members of our galaxy, drifting far from the crowded spiral arms, shining faintly in the darkness at the edge of the Milky Way. Their orbits carry them through regions where stars are few and space is vast. Yet they remain bound, circling the galactic center for billions of years without ever escaping. They are like distant watchtowers, marking the perimeter of our cosmic home, silent witnesses to the galaxy's long and turbulent story. To imagine these outer realms is to feel the scale of the Milky Way in a new way. When we look up at the band of light across the sky, we are seeing the crowded interior of the disk, but far beyond what we can see with our eyes, hundreds of thousands of light years away, these clusters and stars continue to orbit, extending the galaxy's reach into the dark. They are not merely peripheral, they are essential, for without them, our understanding of the galaxy's boundaries would be incomplete. They remind us that the Milky Way is not only the glowing pinwheel of stars we can picture, but also a sprawling, ancient system whose edges dissolve gradually into the greater universe, held together by gravity, history, and the faint light of stars too far to see. Except with the most patient observations, the Milky Way does not exist in isolation. It is not a solitary island of stars drifting alone in the void. Instead, our galaxy is part of a larger cosmic family, bound together by gravity in a collection known as the local group. This community of galaxies, which includes the Milky Way, the Andromeda galaxy, and dozens of smaller dwarfs, constantly interacts in ways both subtle and profound. These interactions blur the very concept of where the Milky Way ends, because the gravitational influence of nearby companions stretches across space, tugging on the outer stars, distorting the disk, and feeding streams of material into and out of the galaxy. To truly understand how far our galaxy reaches, we must recognize that its boundaries are not fixed walls, but shifting zones of gravitational negotiation with its neighbors. The most prominent companions of the Milky Way are the large Magellanic Cloud LMC and the small Magellanic Cloud ZMC, two irregular dwarf galaxies that orbit our own. They are visible to the naked eye in the southern hemisphere as faint, cloudy patches of light, and for centuries they were viewed as curiosities. Today, we know that they are more than just distant companions. They are active participants in shaping the Milky Way. The LMC, in particular, is massive enough to exert a measurable pull on our galaxy, and as it orbits, it creates ripples and warps in the Milky Way's disk. This gravitational tug distorts the otherwise flat plane of the galaxy, producing a warp that astronomers can measure by mapping the positions of neutral hydrogen gas across the disk. In this way, the Magellanic Clouds blur the notion of the Milky Way's edge, since their influence extends deep into the structure of our galaxy. But the interaction is not one-sided. The Milky Way's immense gravity also pulls strongly on the clouds, stripping streams of stars and gas from their edges. One of the most spectacular results of this interaction is the Magellanic Stream, a colossal ribbon of hydrogen gas that trails behind the LMC and ZMC, stretching across more than 100 degrees of the sky. This stream is invisible to the naked eye but easily detected in radio wavelengths, and it shows that material from the clouds is being fed directly into the halo of the Milky Way. Over billions of years, this process has enriched the galaxy with fresh gas, fueling star formation in the disk and ensuring that the Milky Way continues to shine with new generations of stars. In this sense, the Milky Way's reach extends not only through its stars, but through its ability to draw material from neighboring galaxies, absorbing and recycling it into its own structure. The Magellanic Clouds are not the only companions. Surrounding the Milky Way are more than 50 dwarf galaxies, faint and fragile systems that orbit at various distances. Some, like the Sagittarius dwarf galaxy, are in the process of being torn apart by our galaxy's gravity, their stars stretched into vast streams that wrap around the halo. Others, like the Fernax and Sculptor dwarfs, remain intact, but are still heavily influenced by the Milky Way's pull. These galaxies blur the definition of inside and outside when it comes to our galaxy's boundaries. Their stars, their gas, and even their dark matter halos interact with the Milky Way's own halo, creating a complex network of overlapping influences. The Sagittarius dwarf galaxy is perhaps the most dramatic example. Discovered in the 1990s, it was found to be a small galaxy currently being consumed by the Milky Way. Its orbit carries it through the halo, and with each pass, more of its stars are stripped away and added to our galaxy. The resulting streams form great arcs across the sky, weaving through the halo like ribbons of starlight. For astronomers, these streams are not only beautiful, but also useful because they trace the shape of the Milky Way's gravitational field. By studying them, scientists can map the distribution of dark matter and better understand how far the galaxy's reach extends. For the galaxy itself, they are signs of growth and change, reminders that it is still assembling, still evolving. still drawing in its neighbors to expand its influence. At a larger scale, the Milky Way's interactions extend beyond dwarf galaxies to its most significant neighbor, the Andromeda galaxy. Andromeda is the closest spiral galaxy to our own, located about 2.5 million light-years away, and it is on a collision course with the Milky Way. Observations show that Andromeda is approaching us at a speed of over 100 kilometers per second, pulled by the mutual attraction of the two galaxies' immense halos of dark matter. The collision is predicted to occur in about 4 billion years, when the disks of the two galaxies will begin to overlap. Over billions of years, they will merge into a single, larger galaxy, often referred to as Milkomeda. Even though this event is far in the future, its inevitability means that the true boundary of the Milky Way is already entangled with that of Andromeda. Their halos overlap, their gravity interacts, and their future is tied together. This overlapping of halos is a profound reminder of how interconnected galaxies are. The Milky Way's dark matter halo extends hundreds of thousands of light-years, and Andromeda's halo does the same. At these distances, the two halos already touch, meaning that in some sense, the Milky Way and Andromeda are not entirely separate even now. They are part of a continuous web of matter, gradually pulling toward one another, destined to unite. In this light, the edge of the Milky Way becomes less a definitive border and more a zone of transition, where our galaxy's influence blends with that of its neighbor. The local group itself provides further context. Alongside the Milky Way and Andromeda, the Triangulum galaxy is the third largest member, and dozens of dwarfs cluster around the giants. Together, these galaxies are bound into a gravitationally connected system spanning about 10 million light-years. Within the system, each galaxy's influence overlaps with the others, creating a complex dance of orbits, mergers, and interactions. The Milky Way's edge is therefore not simply defined by the farthest star or the faintest cluster, but by the balance of forces within this larger family. Its reach extends as far as its gravity can compete with the pull of Andromeda and the other local group members. And beyond that point, the concept of belonging shifts from one galaxy to another, even at smaller scales. The Milky Way's interactions shape its structure. Streams of stars flow into its halo from shredded companions. Gas is siphoned in from the Magellanic Clouds. The disk is warped and rippled by the gravitational pull of orbiting dwarfs. These processes mean that the Milky Way is not a static structure but a dynamic system, constantly evolving through its relationships with its neighbors. Its edges are not fixed but in flux, shaped by external influences as much as by internal forces. For astronomers, these interactions provide natural laboratories for studying galactic evolution. By observing how the Milky Way consumes dwarf galaxies, how it pulls gas from companions, and how its halo overlaps with Andromeda's, scientists can learn about the larger processes that govern galaxy growth throughout the universe. Every stream of stars is a record of a past event. Every warp in the disk is a sign of an ongoing interaction. Every overlapping halo is a preview of a future merger. Together, they tell a story of a galaxy whose reach is not simply defined by its luminous disk, but by its relationships, its gravitational bonds, and its exchanges with the galaxies around it. And there is also something humbling in this picture. When we think of the Milky Way, we often imagine it as a grand, majestic spiral, standing alone in space. But the reality is far more interconnected. Our galaxy is a participant in a cosmic network, drawing in companions, shaping and being shaped by its neighbors, and moving inevitably toward union with Andromeda. Its edges are therefore not clean boundaries, but porous borders, zones of influence that stretch outward and blend into the larger structures of the local group. The outer stars and clusters may mark one kind of edge, but the interactions with neighboring galaxies redefine that edge again, extending the Milky Way's reach across millions of light-years, not as an isolated system, but as part of a greater whole. When we speak about the size of the Milky Way, it is tempting to imagine the galaxy as a structure with a fixed edge, like a city with a boundary sign that tells you when you are entering or leaving. But the cosmos does not draw such clean lines. Instead, a galaxy's true reach is best described in terms of influence. This influence is most evident through gravity, the invisible force that binds stars to orbit the galactic center, that holds the halo of dark matter in place, and that stretches far beyond the visible disk to shape the environment of the local group. The influence zone of the Milky Way is therefore not limited to the luminous band of stars that we can see in the night sky, nor even to the extended halo of globular clusters. It is a gravitational domain that stretches across unimaginable distances, reaching out into intergalactic space and competing with the pull of nearby galaxies. At the heart of the Milky Way's influence lies its enormous mass. Astronomers estimate that the galaxy contains roughly 1 trillion times the mass of our Sun, most of it in the form of dark matter. This invisible substance does not emit or absorb light, but it makes its presence known through gravity, creating the vast halo that envelopes the galaxy. The halo's radius is believed to extend for hundreds of thousands of light years, perhaps as much as 1 million, encompassing not only the stars and clusters we can see, but also an enormous sphere of gravitational control. Within this region, stars, gas, and smaller galaxies are all subject to the Milky Way's dominance, moving in orbits dictated by its gravity rather than drifting freely through space. The concept of a galaxy's sphere of influence can be compared to the idea of a Hill sphere in planetary science. Just as Earth has a region around it where its gravity dominates over the pull of the Sun, the Milky Way has a region where its gravity dominates over the pull of neighboring galaxies. This sphere marks the true extent of the Milky Way's reach. Within it, objects are gravitationally bound to our galaxy. Beyond it, they may be more strongly influenced by another system, such as the Andromeda galaxy. By this definition, the Milky Way's influence stretches much farther than the starlit disk that defines its visible form. It reaches into the darkness, into the diffuse medium that separates galaxies, binding together a realm much larger than we might imagine when gazing at the sky. One of the clearest examples of this influence is the population of satellite galaxies that orbit the Milky Way. Dozens of these dwarfs, some faint and barely detectable, are gravitationally tethered to our galaxy. They may lie hundreds of thousands of light years away, but they remain bound, tracing slow, elongated paths around the Milky Way's center. The Sagittarius dwarf, the Magellanic Clouds, and a host of smaller systems like Draco and Ursa Minor are all contained within this gravitational zone. Their motions tell us where the Milky Way's gravity is strongest and help astronomers measure the extent of its dark matter halo. Without this halo, many of these small galaxies would escape, drifting into intergalactic space. Their continued presence reminds us that the Milky Way's reach is far greater than its disk alone, but the zone of influence does not end with the satellites we know. Streams of stars, ripped from smaller galaxies and stretched into glowing rivers across the halo, are another testament to the Milky Way's power. These tidal streams can span hundreds of thousands of light years, marking the boundaries of our galaxy's gravitational grasp. They show how the Milky Way actively pulls material from its surroundings, shaping and consuming its environment. Each stream is a record of an interaction, a fossilized trace of the galaxy's influence on its companions. Together, they weave a vast and complex map of gravitational dominance, a map that extends outward to the very limits of the halo. The influence zone of the Milky Way also interacts with that of other galaxies, most notably Andromeda. At a distance of about 2.5 million light years, Andromeda is close enough that its own dark matter halo overlaps with ours. This overlap is a remarkable fact. It means that the two galaxies are not entirely separate entities, but are already part of a shared gravitational environment. Between them lies a diffuse region where the pull of each galaxy competes, where stars, gas, and dark matter exist in a kind of no man's land of cosmic forces. This overlap hints at the future collision between the two galaxies, which will take place in several billion years. In a sense, the Milky Way's influence zone is already entangled with that of Andromeda, showing us that even the largest galaxies cannot exist in true isolation. The question of how far the Milky Way's influence extends also leads us to consider the local group as a whole. This collection of more than 50 galaxies is bound together into a larger gravitational system. The Milky Way and Andromeda are the dominant members, each with their own vast halos of dark matter and their own swarms of satellites. But beyond the local group, the pull of other structures like the Virgo cluster of galaxies begins to dominate. Somewhere between the local group and these larger structures lies a boundary known as the zero-velocity surface, where the expansion of the universe balances the pull of the local group's gravity. Within this boundary, galaxies remain gravitationally bound to one another. Beyond it, they drift away with the expansion of space. The Milky Way's influence, therefore, is not only defined by its immediate halo, but also by its role in this larger gravitational hierarchy. The sphere of influence is not just a matter of stars and galaxies. It also extends to gas and cosmic radiation. The Milky Way exerts control over enormous reservoirs of hot, diffuse gas that fill the circumgalactic medium. This gas extends far into the halo, forming an atmosphere of sorts around the galaxy. It interacts with incoming material, such as the Magellanic Stream, and regulates the flow of gas into the disk, which in turn governs star formation. In this way, the galaxy's influence zone acts as both a shield and a reservoir, controlling the flow of matter across cosmic scales. This medium is also where the galaxy's magnetic fields extend, shaping the paths of charged particles and influencing the cosmic rays that drift through interstellar space. Understanding the extent of the Milky Way's influence is not only an academic exercise, but also a profound exploration of scale. When we look at the night sky, we see the Milky Way as a glowing ribbon stretching across the horizon. It feels vast and complete, as though it contains everything. But in truth, that ribbon is only the inner part of a much larger whole. The disk may span 100,000 light years, but the halo and influence zone extend 10 times farther. The stars we see are only the visible core of an empire of gravity that stretches across nearly 1,000,000 light years, binding together companions, streams, and clouds of gas in a vast and invisible net. For those of us on Earth, it is humbling to realize that we live not only inside a spiral disk of stars, but deep within a gravitational field that extends far beyond what our eyes can see. The Sun orbits the center of the galaxy, carrying us around every 230 million years, but it does so within a framework held together by forces that stretch to distances we can barely imagine. Our home is not just the solar system, not just the Milky Way disk, but an influence zone that reaches into intergalactic space, linking us to neighbors we cannot see with the naked eye and tying us into the cosmic web of matter and energy that makes up the universe. The influence of the Milky Way is also a reminder of how connected everything in the universe truly is. The gravity that holds distant dwarfs in orbit is the same gravity that keeps Earth tied to the Sun and the Sun tied to its orbit around the galactic center. The dark matter that defines the extent of the halo is the same invisible substance that shapes the formation of galaxies across the cosmos. And the future collision with Andromeda, already written in the overlap of halos, is part of a larger story of galaxies assembling into clusters and clusters into superclusters. The Milky Way's influence zone, therefore, is both a local reality and a reflection of universal processes, stretching our sense of place far beyond the boundaries of the visible night sky. When we ask where the Milky Way truly ends, we are asking a question that does not have a single, simple answer. Unlike a solid object with a clear surface, a galaxy is a collection of stars, gas, dust, and dark matter that fades gradually into its surroundings. There is no cosmic signpost telling us that here, definitively, the Milky Way stops. Instead, astronomers must decide how to define the edge depending on what aspect of the galaxy they are studying. For some, the edge is the visible disk where the starlight becomes too faint to detect. For others, it is the outer boundary of the dark matter halo, the unseen skeleton that holds the galaxy together. Still, others may argue that the edge lies where the Milky Way's gravitational influence yields to that of other galaxies in the local group. Each perspective gives us a different boundary, and together, they show that the true answer depends on what we mean when we ask the question. If we start with the visible component of the Milky Way, the disk of stars is the most obvious structure. This disk is about 100,000 to 120,000 light-years across, with our Sun located roughly halfway between the center and the edge. When we look up at the night sky and see the glowing band of the Milky Way stretching overhead, we are looking through the dense parts of this disk. But the starlight does not end suddenly at its edge. Instead, the density of stars gradually decreases, thinning into the outer disk. Beyond this lies the galactic halo, a faint region containing old stars, globular clusters, and streams of material stripped from dwarf galaxies. If we were to define the edge of the Milky Way purely by visible stars, we might set it at around 150,000 to 200,000 light-years from the center, where the stellar density becomes extremely low. Yet even here, the galaxy is not truly finished. The halo extends much farther than the visible disk, and it is filled not only with stars, but also with dark matter. Dark matter cannot be seen directly, but its gravitational effects reveal its presence. Without it, the stars at the edge of the disk would not orbit as fast as they do. They would fly off into intergalactic space. Measurements of stellar motions and satellite galaxies suggest that the Milky Way's dark matter halo stretches as far as 1 million light-years from the center, making it 10 times larger than the visible disk. This halo is diffuse and invisible, but it is the dominant structure, containing far more mass than the stars and gas combined. If we define the edge of the galaxy as the extent of its dark matter halo, then the Milky Way is far larger than most of us imagine when we picture it in the night sky. The concept of the halo edge is, however, not sharp. Unlike a surface or a border, the dark matter distribution gradually fades into intergalactic space. Astronomers sometimes define the boundary as the point where the average density of dark matter drops below a certain threshold relative to the background density of the universe. By this measure, the edge is called the virial radius for the Milky Way. The virial radius is estimated to be around 200,000 to 300,000 light-years, though some calculations suggest it could extend as far as 600,000 light-years. Within this radius, the galaxy is considered a self-contained system in gravitational equilibrium. Beyond it, the halo's influence becomes weaker, though not absent, blending into the larger structures of the cosmic web. Another way to think about the edge of the Milky Way is in terms of its gravitational dominance. The galaxy is not alone. It exists in a crowded cosmic neighborhood. The Andromeda galaxy, our nearest large neighbor, lies about 2.5 million light-years away, and its dark matter halo is just as vast as ours. At some point between the two, the gravitational pull of Andromeda becomes stronger than that of the Milky Way. This point marks a practical boundary of influence. Astronomers estimate that the halos of the Milky Way and Andromeda already overlap, meaning that in some sense, neither galaxy has a completely independent edge. They are locked together, their invisible halos entangled, foreshadowing their eventual collision and merger billions of years in the future. If we define the edge by gravitational competition, then the Milky Way does not end in isolation, but in a region of shared control, where its reach transitions into that of Andromeda. The presence of satellite galaxies further complicates the question of where the Milky Way ends. Dozens of small dwarf galaxies orbit the Milky Way at distances of tens to hundreds of thousands of light-years. Some, like the Magellanic Clouds, are prominent companions. Others, like the Sagittarius dwarf, are in the process of being absorbed. These satellites exist well outside the visible disk, yet they are still part of the Milky Way system, bound by its gravity. Their orbits demonstrate that the galaxy's influence extends to great distances. But should we consider them inside the Milky Way or outside it? They are separate galaxies, yet also part of the Milky Way's gravitational domain. Their existence shows that the concept of an edge is less about a physical line and more about the dynamic relationships between objects bound together in space. The streams of stars torn from these dwarf galaxies also trace the boundaries of the Milky Way. As smaller galaxies are disrupted, their stars are stretched into long, curving streams that arc across the halo. These streams can reach hundreds of thousands of light years from the galactic center, blending into the intergalactic medium. By following these structures, astronomers can map the gravitational reach of the Milky Way and gain clues about where its influence begins to wane. But even these streams do not mark a definitive end. Instead, they show us a gradual transition, a blending of structures across enormous distances. The gas surrounding the Milky Way adds yet another layer to the question. Observations with space telescopes have revealed the presence of a vast circumgalactic medium, a diffuse envelope of hot, ionized gas that surrounds the galaxy out to distances of several 100,000 light years. This gas is not bright enough to see directly, but it leaves imprints in the spectra of distant quasars, where it absorbs specific wavelengths of light. The circumgalactic medium contains enough material to rival the mass of all the stars in the galaxy, and it acts as a reservoir that feeds star formation in the disk. If we include this gas, then the Milky Way extends far beyond its visible stars, occupying a much larger region of space. But again, the transition is gradual. The density of gas declines slowly with distance, fading into the intergalactic medium. The edge is not a surface, but a zone of thinning material. All of these perspectives show that defining the end of the Milky Way is as much a philosophical challenge as a scientific one. If we define it by visible stars, the edge lies at the faint outer disk. If we define it by dark matter, the edge extends nearly 1,000,000 light years. If we define it by gravitational dominance, the edge lies somewhere between us and Andromeda. If we define it by gas, the edge is an envelope of hot plasma fading into intergalactic space. Each answer is valid in its own way, and each highlights a different aspect of what a galaxy truly is. This ambiguity reflects the nature of galaxies themselves. They are not solid objects, but dynamic, evolving systems. They are constantly pulling in material from their surroundings, interacting with neighbors, and shedding streams of stars and gas. Their boundaries are porous, flexible, and changing over time. The Milky Way we see today is not the same Milky Way that existed billions of years ago, nor will it be the same billions of years in the future. Its edge is always in motion, always being redefined by the flows of matter and energy that sustain it. For us here on Earth, the question of where the Milky Way ends is less about a physical boundary and more about a shift in perspective. It reminds us that our galaxy is not an isolated island, but part of a continuum of structures in the universe. Its edge is not a wall, but a blending place where its influence fades and merges with that of others. To ask where the galaxy ends is to confront the vastness of space, the gradual transitions that define cosmic structures, and the interconnectedness of everything that exists in the universe. When we step outside on a clear night and look upward, the Milky Way appears to us as a glowing river of light stretched across the darkness. It looks like something that might be close, something we could almost reach out and touch. If only we were higher, if only we could climb into the sky. But this perception is a trick of scale. The light we see is made up of billions of stars, each separated from the other by vast gulfs of space, and the faint glow itself is only a glimpse of the galaxy's inner disk. The true reach of the Milky Way extends far beyond what our eyes can take in, far beyond what even the most powerful telescopes can show us directly in a single image. When we ask ourselves how far the galaxy reaches, we are also asking how far our imagination can carry us. Because the numbers involved are not just large, they are beyond ordinary comprehension. For instance, the very concept of a light year is already a stretch for human intuition. A light year is the distance light travels in 1 year, nearly 6 trillion miles. Even the closest stars beyond the sun are several light years away. Distances so immense that if you could travel at the speed of a modern jet plane, it would take tens of millions of years to reach them. In this way, the perspective of distance becomes not just a scientific matter, but a human one. It shapes how we think about our place in the cosmos, how we tell stories about the universe, and how we find meaning in the vastness of space. To ask how far the Milky Way reaches is to ask how far we are willing to stretch our minds, how far we are willing to expand our sense of home. It is an invitation to step outside the familiar and to embrace the immensity of existence, not with fear, but with wonder. Because the edge of the galaxy is not only a physical distance, but also a boundary of imagination, a place where measurement meets mystery, and where human curiosity meets the infinite. As we have traveled together through the quiet corridors of the night sky, tracing the spiral arms of the Milky Way, crossing its stellar disk, and drifting into its vast dark halo, we have slowly begun to appreciate what it means to live inside a galaxy of such immense proportions. From the stars visible in our backyard sky, to the unseen currents of dark matter shaping its structure, the Milky Way is more than just a collection of stars. It is a living system, dynamic and evolving, stretching across distances that challenge the very limits of human comprehension. We began by exploring the visible heart of the galaxy, the radiant band of stars and gas that has inspired myths, guided travelers, and awakened curiosity for countless generations. We then pushed outward into the disk, a realm of rotation and gravity where our sun and billions of other stars orbit the galactic center in a slow, majestic dance. We looked beyond the bright edges into the hidden halo, where ancient globular clusters and invisible streams of dark matter extend the Milky Way's reach far beyond what our eyes can see. We considered how the galaxy itself does not end in a clean border but blurs into neighboring systems, merging its gravitational influence with Andromeda and the other members of the local group. In this way, the Milky Way is not an isolated island, but part of an intricate web of galaxies stretching across the cosmos. Its edge is not a fixed boundary but a frontier, expanding and changing as it absorbs new material and interacts with its neighbors. And through it all, we have returned again and again to the humbling fact of scale. Light, the fastest thing in the universe, requires hundreds of thousands of years to cross our galaxy. Human history, in comparison, is less than a flicker of time, and our world occupies only a small corner of one spiral arm. Yet this does not diminish us. Instead, it gives our existence a context filled with wonder. To know that we are part of something so vast is to understand that our story is not just Earth's story, it is the story of the Milky Way itself. For us, the question of how far our galaxy reaches is both scientific and deeply human. Science gives us the numbers, the models, and the boundaries, but imagination gives those numbers life. It allows us to picture the glowing spiral of the Milky Way as if seen from afar, to imagine traveling beyond the halo into intergalactic space, and to feel the awe of distances that stretch far beyond what our senses can grasp. In this sense, the Milky Way's reach is not only measured in light years, but also in the reach of our minds, our curiosity, and our dreams. As we close our eyes tonight, and let these thoughts drift into the quiet of sleep, we can carry with us a new perspective, that we are at home in a galaxy of extraordinary size and beauty, a galaxy that connects us to the greater universe, and a galaxy whose true reach lies not only in the stars, but in the boundless capacity of human wonder.